Okay, so let me go through a problem because this one is I want to go through a couple problems. I'm going to do two problems, which will be related to what you'll see on the exam. That's why I'm doing them. So this is an equilibrium problem. So here we have this is a gas phase reaction. A plus 2B going to C plus D. And what I should say, I'll add this. I should not do it in that color though. Let's do this color. I didn't say this, but if I don't say it, it's because I forgot to say it. So please, if it's a gas on the final, it's going to be an ideal gas. So we assume it's ideal. Okay. And so write down the reaction Gibbs free energy, delta R sub G of the system, in terms of and I'm going to add to this and send it again to you, okay? So I'm going to send you the same file that I sent this morning, but it's going to be this whole lecture. It'll be the lecture file. Okay, in terms of the standard molar Gibbs free energies, and the standard molar Gibbs free energies are these chemical potentials, mu sub J naught, that funny naught. The partial pressures of the gas is P sub J, the standard pressure, P naught, and the temperature. And so what is that molar free energy? This, and like this and this will be on the exam. Okay, they'll be on the back of the exam, but there's lots of stuff back there. So, if you forget if it's ends or mu, so you shouldn't miss this. But some people probably will. It'll be the formulas will all be there. Okay, but you just have to use it here and know that this is what you want. And it's this weighted average with the stoichiometries of the chemical potentials, right? And if we work that out, we get this thing, right? And you might remember G is the sum of N sub J mu sub J, but dG is the sum of N sub J mu sub J dN sub J, right? And dN sub J was nu sub J times C. And so there was a lecture, and it's in the book, and you've seen why it's this thing. And I didn't ask you why it is, but you should know, that it's good to know where this came from. Go through the derivation. You're not going to be deriving it, but it helps to know why it's this thing, and here it is. So we put it together, and I'm trying to be careful to answer my own questions correctly. And so here's what I wanted. And there was some algebra that went into putting it all like that. I could have written out all those terms separately and not combine the logarithms. And that would be okay, because if your lawyer was with you, they would say, well, the answer is in terms of what he asked for, and it wasn't wrong, so that would be okay. That doesn't mean the TAs wouldn't take points off, but that's why there are lawyers, right? Yeah, there's a question? Well, let's look at it. You got to be careful with the P naughts, but every factor has a P naught paired with it. Okay, if I wrote it all with the P's, then there would be the P naught would not cancel. So the P naught is still in there, but I just happen to keep it in that form. And why did I do that? Because it'll make life easier later. And I grouped it. I just I leave it like that. Why? You know, like you're saying you're going to clean it up and cancel out stuff. Every time you do that, you're asking for trouble because you can make an algebraic mistake. So I like this form because I get to the second part here, and I'm kind of ready to do that. Write your answer to A. Okay, so here's my answer to A in terms of the standard reaction-free energy and the reaction quotient Q, and give expressions for these two quantities. That was a little bit not the most elegant grammatical, wasn't beautiful prose, but here's what I wanted. You know, I wanted this, and you know this is always true, right? And this will be on the exam. This will be on the back of the exam too. This is always true. But then, you know, what are the pieces? This piece is that piece, right? It's the difference. And you notice there's ones in front of everything, but there's a 2 in front of the B, okay? And it's a reactant. And so there's ones everywhere. The products have pluses. The reactants have minuses, and there's that 2 in front of the B that is always showing up places. And here we have powers of 1 everywhere except at the B. It has a power of 2, and because it's a reactant, it's in the denominator, right? Along with the A. The A and the B are reactants, are in the denominators. And so I write this thing that's always true, and then I say where, and I'm getting, I'll give expressions for these quantities. So Q is that thing, and I already had it here, right? I packaged it, and then here is the standard state reaction Gibbs free energy. Now this is an easy question, but the cost of easy questions are sometimes people get it could be. I think it's clear, but I just wrote this out this morning, so maybe it's not as clear as I would try to make it on the exam. But don't find it confusing because it's simple. Okay. Let's and this is walking you through it. So now I move on to part C, and I say the equilibrium constant for this reaction is K equals 10 to the minus 3. And this is not your first rodeo. There's a guy on TV that has Medicare commercials or some reverse mortgages. You find an old guy that's famous, and then you put him on a commercial, and everybody believes him, right? And he said this reverse mortgage was not his first rodeo. Equilibrium constants, they're not your first rodeo. You know, if you have an equilibrium constant, and you knew this in general chemistry, if it's equal to, if it's big, if it's like 10 to the 8th, how is the reaction at equilibrium? Do you have a lot of products and few reactants? Do you have a lot of reactants and few products, or do you have equal amounts of reactants and products, just roughly speaking? So this equilibrium constant's pretty small. Which way is the reaction, just intuitively? It's mainly to the reactant side, right? So the products, not so many products. If K was 10 to the 8th, then there would be almost all products and very little reactants, right? Because Q at equilibrium, so the pressures of C and D in units of this P bar, the numerator's small compared to the denominator. The numerator's 1,000 times smaller than the denominator at equilibrium, because Q is equal to K at equilibrium. So if you see that number, you should immediately think, this reactant's not going to be too far to the right. It's going to be mainly to the left. But let's see if that bears out in my calculations. So I prepared an initial mixture of gases prepared at the following partial pressures. So A, B, C, and D are all prepared at their standard state. okay? Now, I forgot to put this one in, and I might have even put that one before the pressures. But I've given you this. This is asking you just to think about what that equilibrium constant is telling you. Well, I talked about what it's telling you kind of just pictorially, intuitively, and now we're going to see what the consequences of that equilibrium constant is for the standard state, because we know, and again it'll be on the back of the exam if we don't, that the standard reaction Gibbs free energy is minus RT log K, which is minus RT log of 10 to the minus third. It would be easy to take that logarithm if it was e to the minus third, but it's 10 to the minus third. But still, now you can use your, please, if you want, if your calculator helps you doing what I'm about to do, by all means use it. But for me, every time I put my fingers on a calculator, calloused from playing the banjo as they are, put them on the calculator, I'm gonna make, that's another room for error, right? So, because you know the answer, but you push the wrong button. So minus RT log of 10 to the minus 3 is plus RT log of 10 to the 10 cubed. So it's R times T times the log of 1,000. Now, is that positive, negative, or equal to 0? So R is positive, T is positive. The logarithm of 1,000. Get your calculators out. It's positive, right? It's pretty big. But it's logarithms are a lot smaller than the things you're taking the logarithm of. But it is positive. And does that make sense? So if I make, I'm always, you always be reality checking yourself. So this is the reaction-free energy at standard conditions. And if I were at standard conditions, I have a reaction delta G that's positive. Which way do I want to go? I make a cocktail, a gaseous cocktail. It's an oxygen bar with some nitrous oxide for good measure. Like you go to tell you, if you're making paella up in the mountains, see, we talked about the boiling point being lower. If the rice doesn't cook, you just go down the street. There's an oxygen bar, because there's all these rich people that go to Telluride, and they need their oxygen because they're from Los Angeles. And nitrous oxide you can mix with that. You make a cocktail of gases. That's what I'm getting at, and they're all at one atmosphere. There's A, B, C, and D, and I calculate reaction delta G. I didn't ask this yet, but what's going to happen? Is this going to stay like that? Is it going to go forward, or is it going to go backwards? It's going to go backwards, right? And that's so okay. At standard state, the delta G is positive, so it wants to go backwards. This is consistent with my reality check. The K is 10 to the minus third, and I'm not expecting a lot of products. So if I have equal products and reactants, it makes sense. It's going to go backwards. So I'm feeling okay. I know some of you panic, and for a 2-hour final, you can panic for a whole hour and still have time to finish it. But if you're thinking like this, then you're not going to panic as much because it's making sense. Now look, this part here, and I would number this differently. Like I said, I prepare an initial mixture, which is actually at standard conditions. Okay? And so I say find the reaction-free energy at these conditions. You do not need to evaluate logarithms. Give your answer in terms of delta R, this thing, delta G of reaction, not R and T. I could have said, calculate Q, if I wanted to walk you through. And probably I would do that on the exam, because there's a lot of little parts, right, to make sure. So I calculate Q, and everywhere I see a P, a PC, a PD, a PA, and a PB, I put P naught in. And so I've got P naught over P naught, P naught, P naught over P naught, P naught over P naught, P naught over P naught squared. That's pretty good. I said that pretty fast. After a lot of algebra, I get 1. So the Q is equal to 1. And if I put that in here, it turns out delta G of the reaction is actually equal to the delta G at the standard state of the reaction. That's what I get. How could I get that? See, this is where people start worrying that they're not doing it right. Right? This Martens, he always asks these odd questions. But I ask you to prepare it at standard state. So you could say, hey dude, this guy's doing it at standard state. And so I'm expecting to see that later, and there it is, right? It's the delta G is the delta G at standard states. And then I ask you, okay, so I do that, and I ask you if it was, so here, it's equal to, here's the number, it's RT log 10 cubed. And we already convinced ourselves that that's positive. And you don't have to, this is, leaving it as log of 10 cubed is fine with me, right? And because, I don't have it. Well, I actually do have a calculator, because I'm going to steal the one that was left here if nobody else takes it. It's right here, by the way. But I would put it in Mathematica and think of A.J. Shaka and hit return. I get the number. And it would be positive. So I ask you, what will happen? Okay? And I say select one. And so this is a multiple choice. It proceeds in the reverse direction, as we've already discussed. And this happens, of course, because the delta G of the reaction for what I actually prepared happens to be at standard state, and it happens to be positive, and so it's going to go in reverse. Now, okay, so if you didn't know how to do that part, this is why these multi-step questions are not necessarily always good. But let's well, here it is. That's what it is. Repeat part C, but with an initial composition where I make the reactants only 0.1. Okay, and the products are 1. So I'm using 1/10 as well. A partial pressure that's 1/10 for the reactants. Oops, I did this wrong, because. Let's fix this. This is what happens, because there's a 0.1 and a 0.1 squared. So that's 10 to the plus 3, right? Yeah, let's I'm going to send this to you, so let's fix this so that it's what I wanted. Let's keep these. My apologies. This is what happens, right? Let's make P sub C, 0.0. 0.01 P naught. Should be up higher. And PD, yeah, 0.1. 0.1 P naught. And then we get rid of these down here. And then we have let's just get rid of the top. 0.01 P theta over P theta. 0.1 P theta over P theta, whatever that is. And then this is now what I wanted. This is because the punchline. Yeah, if I was a stand-up comic, I'd be off the stage by now. But it works a little bit different here. So so now I have 10 to the minus 3 for the Q. That's what I wanted. So so now we proceed. Okay, I think that's right. We have our Oops, apologies for that. Oops. This thing is this delta G naught plus RT log Q, delta G naught plus RT log. And I wanted that was 10 to the minus 3. I think I changed that one too. Oops, close enough. And if I work everything out, because this I have delta G R naught plus RT log K, right? Because my Q is equal to K. Let me add this here. Oops. Q equals K. And so when I go through it, my delta G of the reaction is equal to 0, because that's how we get 0 equals, that's how we derive that delta G of the reaction at standard conditions is minus RT log K. So I prepared a mixture, and when I did it right and didn't get the wrong power here, I'm glad I saw that. It would be hard to try to explain why it was working out this way. So I prepared the Q not at standard state but at K, and then that means that the reaction's actually at equilibrium, because the partial pressures are such that if I put them in the reaction, my Q would be equal to the equilibrium constant. And so the answer to the forward, backward, or unchanged would be unchanged. Now, you could also do this problem, and this is the way we did it, the way I did it. I don't know if anybody else was following. But in general chemistry, there were some rules that we remember. So like if Q equals K, so Q is what you have, K is the equilibrium constant, and you want to go there, right? If Q is equal to K, you're already there, right? If Q is bigger than K, you want to change things to make Q be K. And if Q is greater than K, that means that Q stands for quotient, which is a fancy word for stuff on the numerator and stuff in the denominator. It's actually much shorter than saying that. And if Q is bigger than K, that means the numerator is too big and the denominator is too small. The numerator is products and the denominator is reactants. So if Q is bigger than K, you want to make the numerator smaller and the denominator bigger, and that means you want to go backwards, right? If they're equal, you're okay. That's unchanged. Hopefully by context you can figure it out. And if Q is less than K, then you want to go forward to make the numerator bigger. Okay. I mean, any questions aside, how did you get this job on this one? If not, okay, so I'll send this updated one to you. And something like this. will most likely show up. Remember, and I also promised you this kind of picture, kind of situation, right? So we have point A and B, and this is some constant pressure. So I'm going from A to B. I'm raising T at constant P. So what is this? So here's a picture. What is it? Where did this picture come from? What do they call it? Yeah. So what are these areas? What are these? Like high pressure, low temperature, this is solid, right? And if you're an engineer, my apologies for, but if you're a material scientist, there's lots of phase transitions of all kinds of different alloy phases and stuff, and you can have all kinds of complicated phase diagrams. This is the only one that we're going to talk about. But if I go from A to B, I start in the liquid and I get to this gas phase. I cross these, what are these lines called? Do they have a name? Yeah, they're phase bound. Yeah, they're phase boundaries. There's phase boundaries. Now this is where sociology and anthropology and politics differ from science. Along the phase boundaries, we have coexistence, which means that like here mu solid is equal to mu gas, and et cetera, right? And at this point, mu solid equals mu liquid equals mu gas, and so there's triple point, critical point, phase boundaries, and those are like coexistence curves, coexistence lines. If you go to the boundary between two countries, is that where you find coexistence? No, that's where the most guns are. Okay, so the analogies only go so far. But if I go from A to B, and Saurabh should be here soon with some exams, and he'll save the day. But I can plot. Oh, and by the way, what's this point here called? Hint, it's T sub B. What is that point? Boiling point. Okay, so I can graph things. I can graph the volume. I could graph the enthalpy. I could graph the entropy, and I could graph the chemical potential as I go. So this is one of my favorite questions. So I don't know if I could even resist not putting something about this. Like I'm going from liquid to vapor, liquid to gas, and I'm plotting. These are all molar quantities. So the molar volume, the volume of 1 mole, the enthalpy of 1 mole of, let's say it's water, the entropy of 1 mole of water, the chemical potential, etc. And I'm plotting that as a function of temperature. Things expand, right? So I heat up water, expands a little bit. Actually, what happens when I freeze it though? What happens? It expands more. So you have to be careful. But the vapor, it's just down here, okay? if I take liquid water, turn into vapor, what happens to the volume of 1 mole? It gets bigger. Right, so we've got these jumps. And what about the entropy? 1 mole of liquid water has an entropy. 1 mole of water vapor has an entropy. Yeah, before this class you would have had no trouble answering that question. But at T sub B they jump. What about the enthalpy? That's a little bit more subtle, I guess. But if I have liquid water, if I had, yeah, there's a jump again, but yeah, so the thing to memorize is there's always jumps, right, or whatever. But this jump here is the latent heat of water. If I have 1 milliliter or whatever, this you probably I have to check the number. I'm not going to say it. It's probably equal to 1, but better be careful. I think this might be why the calorie has the definition it does. But if I have a certain amount of water, it's a liquid, and I want to convert that to one at same pressure, whatever. I want to convert it to 1 same amount of vapor. I have to add heat to it, and it's a famous number. And that's the latent heat, and that's what this jump is here. I don't think I even used the word latent heat before. I'll just say if this is Q, the heat that you have to add. And so the enthalpy goes up by the amount of heat you added. What about the chemical potential? The TAs are sharpening their red pens, right? What does that do? Right, because remember d mu is minus s dt, and this slope equals minus the s of the liquid. Here's the s of the liquid. So if you had graph paper and numbers, you could actually make a graph that had the right slopes. Then we hit that boiling point, boom, right? And that's the slope is minus s of the gas, which is higher, right? And right there, mu sub liquid equals mu sub gas on the border, the phase boundary, the coexistence line. All right. Yes, question. Yeah, I don't know. I mean, why not just draw it? I don't know. I mean, there's pluses and minuses. But this is another one that I'll definitely include. So I think it makes sense. I think it's a good, and it's not an Atkins, is it? Does he have these plots in there? I don't think he does. Yeah, he should. Okay, so I wanted to make sure I talked about those for you. What else do you want to talk about? Anything? Yeah.
Well, questions that were on the previous pictures, could those pop up on the file? Or we've already covered them, they're not.
They could pop up. I suppose they could pop up. I mean, frankly, psychologically, I'm just thinking out loud. Maybe I shouldn't do that as much as I do. But I would be tempted not to. I'd be tempted to sample the question space more broadly. So okay, so we could chat if you still want your exam, just come up and get it while we're chatting. But you keep asking questions. But I would say that one of the best ways to study is to make sure that you understand everything that was on the, I mean, aside from the term, of course, the terms are important too. Did he, okay, I hope he has the SC ones in there. Yeah, it's important to know what the terms are all about, but we're not going to ask them. But there's elements of exam questions from before. There will certainly be the elements of exam questions on the final. It's like Lego pieces, same Lego pieces, and they'll be just maybe assembled in a little bit different way. Yeah. Any other questions, or do you want to just get out of here? What?
Finally, you want to bring the top of the old problems or not? Honestly,
What?
all the examples
Not verbatim, but study the old questions. Yeah. Study the old questions. All right, I guess you guys could get out of here. If you have, I will be around next week. I'll let you know sometimes that I'll actually be drinking coffee at the Phoenix